Hi, my name is Thomas Raman and we are Team 9. The purpose of the Ground to CubeSat Optical Communications project is to determine the possibility of on-off gain modulation to be utilized in air-to-ground communication with the use of off-the-shelf equipment, which include a field programmable gate array, also known as the FPGA, a 10 gigabit per second transceiver, an acousto-optic modulator, also known as an AOM, two variable optic attenuators, and various fiber optic cables. Forward error correction via the FPGA will be used to test the validity of the project, while interleaving will be needed to take into account environmental effects simulated by a modulator. The fall semester involves ordering the required hardware and software and then assembling them together, while the spring semester required the team to begin error correction and collect data throughout various voltage ranges on the modulated condition to determine attenuation. Once that is done, the data is analyzed to determine optimal conditions to achieve specifications as outlined. Thank you.
Hi, I'm Ted Waisaki, and I'm going to do an overview of the hardware used in our project. Here we have the brains of the operation, the Labview Controller. This software, written by the team for this test, can automate the collection of hundreds of data sets that we plan to capture. The Labview controls the voltage output to the VOA, more on the VOA in a moment, with the ability to choose the voltage range, step size, and number of steps to collect in a data set. Labview also records the system throughput power, received transceiver power, error rate, timestamp, and voltages. Finally, all this data is exported into a comma-separated value array. This device is our BERT, or Bit Error Rate Tester. This device houses our transceiver and generates a test pattern to the transceiver at 10 gigabits per second. This pattern is then transmitted through fiber optics to the rest of the test setup. When the signal returns, the number of missed bits is tracked, and the bit error rate is generated. This information is then exported to Labview when commanded. Then, the device resets as a new voltage is set to the VOA to start the error rate calculation over again at a new environmental condition. The small device shown at the bottom center of the screen with the blue pen pointing at it is the VOA, or Variable Optical Attenuator, and also a voltage follower board is shown in the center of the screen. The voltage follower circuit is needed to drive the VOA. The circuit takes the input from the analog output of Labview and drives the power supply to the desired voltage. The VOA will reduce the amount of light allowed through the system fiber based on the voltage value at its input terminals. We can reduce the amount of light through the system up to minus 30 dB, or 1,000 times the input, by sending a voltage from 0 to 5 volts to the VOA. This is how we simulate loss in the atmosphere to a signal traveling in free space. We also have our power meter to measure the amount of power after the VOA, and our DAC, or data acquisition device, to drive the voltage follower board. Once the data has been collected, we can put it into a spreadsheet and then use that spreadsheet to turn the data into graphs explaining our results for the different tests that we've run. And that concludes the overview of our hardware. Now on to Jessica.
Thank you, Ted. Hello, I am Jessica Columbus, and I'm going to go through the results of the data analysis. Using a two-factor analysis of variance test, it was determined that there was no significant difference in the data collected at various time intervals, 1, 3, 5, 10, and 15 seconds. The data collected at 15 seconds, because of the nature of it, took overnight, whereas the 1 second test took only a few hours. It was found that the 1 second test is preferable since the data collected is equally accurate. The second point is that the power at which the bit error rate was above the acceptable industry standard of 10 to the minus 9 was at 100 microwatts. That power is approximately a ninth of the starting power, and the plan is to lower that power even further using error correction techniques.
Thank you, Jessica. My time on the project was spent determining how to best implement forward error correction using the Kintex UltraScale FPGA provided to us by Fibertech. Due to the time constraints of our senior design class, we determined the best course of action would be to try and implement pre-built modules that could be purchased through Xilinx for each of the core functions of the forward error correction process. Fibertech purchased a Reed-Solomon encoder and decoder module, as well as an interleaver-deinterleaver module. The modules purchased through Xilinx come preloaded with example modules in order to test the functionality of your hardware implementation. Unfortunately, we were never able to get any of the example designs to create a stable link between the FPGA and our GTH transceivers. However, Fibertech now owns all of the necessary modules to implement forward error correction using the Kintex UltraScale FPGA. And that completes our demonstration video. Thank you.